welcome to this problem walkthrough. In today's session, we'll be exploring problem number 519, titled Random Flip Matrix. We'll dive into the problem statement, analyze the brute force approach, and break down the solution step by step. Let's get started. In this problem, you are tasked with working with a binary matrix of dimensions mxn, where all the values initially start as 0. Your goal is to implement a solution class with three distinct functionalities. First, the constructor solution, int m, int n, initializes the matrix with the given number of rows and columns. Then, the flip method flips a random cell from 0 to 1 and returns its position as row call. Importantly, each call to flip must result in a unique cell being flipped until the entire matrix is filled with 1s. Lastly, the reset method restores the matrix to its original state, where all cells are reset back to 0. This setup ensures that you can repeatedly manipulate and reset the matrix while maintaining randomness and efficiency. Now, let's take a look at an example to better understand how the solution class operates. Suppose we initialize an object with solution 3, 1, creating a matrix with 3 rows and 1 column. When we call the flip method, it randomly flips a 0 to 1 and returns the position of the flipped cell. A second call to flip flips another random 0 to 1. After that, by calling the reset method, the matrix is restored to its initial state, where all cells are 0. Finally, calling flip again flips a random cell to 1. Each method call demonstrates the core functionality of the solution class. To delve deeper, let's break down the behavior of the example step by step. Initially, the matrix is entirely filled with zeros, represented as 0, 0, 0. When the flip method is called for the first time, a random 0 is flipped to 1. For instance, the cell at position 1, 0 might be flipped, resulting in the updated matrix 0, 1, 0. On the second call to flip, another random 0 is flipped to 1. For example, the cell at position 2, 0 might be flipped next, giving us the matrix 0, 1, 1. These flips are performed randomly and ensure that no cell is flipped more than once. After the 2 flips, the reset method is called. This function sets all values in the matrix back to 0, restoring it to its initial state 0, 0, 0. Once the matrix is reset, a subsequent call to the flip method again flips a random 0 to 1. For instance, the cell at position 0, 0 might be flipped, resulting in the updated matrix 1, 0, 0. This demonstrates the cycle of flipping, resetting, and flipping again, while ensuring randomness and maintaining the integrity of the matrix. Let's explore another example with a 2x2 matrix. We start by initializing the object with solution 2, 2. Next, we call the flip method 4 times to flip all cells in the matrix. The order of the flips is random, but one possible sequence could be flipping 0, 0, 1, 1, 1, 0, and 0, 1. Each call flips a unique 0 to 1 until the entire matrix is filled with 1s. After these 4 flips, the matrix becomes 1, 1, 1, 1. At this point, all cells have been flipped, and no further flips are possible until a reset is performed. To continue, once the reset method is called, all cells in the matrix are restored to their initial state of 0, resulting in 0, 0, 0, 0. After resetting, a new call to the flip method randomly flips a 0 to 1. For example, the cell at position 0, 0 might be flipped, resulting in the updated matrix 1, 0, 0, 0. This example highlights how the flip and reset methods interact to allow repeated random flipping while maintaining the integrity of the reset functionality. Finally, let's consider the problem's constraints and edge cases. The dimensions of the matrix are constrained such that 1 equals m, n equals 10^4, and the total number of cells will not exceed 10^6. Additionally, there can be at most 10^4 calls to the flip and reset methods combined. The order of flips must be uniformly random, ensuring fairness in the selection process. For edge cases, in a single-cell matrix, the first call to flip will always return 0, 0, and resets will behave predictably. For maximum-sized matrices, the implementation must be efficient to handle large-scale operations within the given time constraints. Repeated resets should always restore the matrix to its initial state, and after all cells are flipped, further calls to flip are invalid until a reset is performed. This ensures robustness and correctness under all scenarios. To solve the random flip matrix problem, we first consider the brute force approach. Here, we maintain an actual 2D matrix of size m by n, where each cell is explicitly tracked. The idea is straightforward. To flip a 0 to 1, we randomly generate indices I and j, check if the cell at matrix I, j, is 0, and if so, flip it to 1 and return the indices. If the cell is already 1, we continue generating random indices until we find a valid 0 to flip. Resetting the matrix is simple. We just reinitialize all cells back to 0. While this method is easy to understand and implement, it becomes inefficient as the matrix size grows. The repeated generation and validation of indices can lead to high time complexity, especially as more cells are flipped. For large matrices, this inefficiency becomes a significant drawback, both in terms of time and space. Now, let's examine the optimized approach using hashmap with index mapping. Instead of maintaining the entire 2D matrix, we can think of it as a flattened 1D array of size m times n. Each cell in the original matrix corresponds to a unique index in this linear representation. To flip cells efficiently, we use a hash map to track mappings for flipped indices. Initially, all indices from 0 to m times n-1 are valid. During a flip operation, we randomly select an index k from the remaining valid indices. Then, we swap k with the last available index in the valid range and record this mapping in the hash map. This ensures that flipped indices are not reused. Finally, we reduce the range of valid indices by decrementing the total count. Resetting the matrix is straightforward, just clear the hash map and reset the valid range. The key insight here is that we avoid maintaining the full matrix in memory. By treating the matrix as a linear array and tracking flipped indices with a hash map, we achieve both random access and efficient updates, saving time and space compared to the brute force method. This optimized method is chosen because it strikes the right balance between efficiency and complexity. Each flip operation averages O(1) time since random selection and hash map operations are constant time. In terms of space, we only use O(f), where f is the number of flips, which is far less than the O(m times n) required for large matrices in the brute force approach. However, there are trade-offs to consider. While the brute force method is simpler to implement, it becomes prohibitively slow and memory-intensive for larger matrices. On the other hand, the optimized index mapping approach is more complex but delivers significant improvements in both time and space efficiency. This makes it the preferred solution for handling the random flip matrix problem, especially when working with large-scale inputs. To tackle the random flip matrix problem, imagine we are given an m by n matrix, where all cells initially contain zeros. Our goal is to design an efficient algorithm that flips a randomly selected 0 cell to 1. Once flipped, that cell should remain 1, and the algorithm must ensure that the randomness is uniform across all available 0 cells. This means every 0 cell should have an equal chance of being flipped. Now, dealing with a large matrix efficiently is critical, as we want to avoid unnecessary computations while guaranteeing this uniform randomness. Here's how we can approach this. First, instead of explicitly managing the entire m by n matrix, we can represent it as if it's a single-dimensional array with a total of m multiplied by n cells. This flattened representation simplifies the problem because we can think of selecting a random 0 cell as simply selecting a random index in this virtual array. Then, we dynamically track flipped cells using a mapping structure, which avoids the need to repeatedly check or modify the actual matrix. This mapping allows us to handle flips efficiently and ensures no redundant operations. To implement the algorithm, we start by initializing a dictionary, called flipped_map, that will dynamically track which indices have been remapped. We also maintain a counter called remaining_zeros, which starts at the total number of cells, m times n, and decreases as cells are flipped. When performing a random flip, we generate a random integer k between 0 and remaining_zeros minus 1. This k represents a random index in our virtual 1D array. If k has already been remapped in flipped_map, we use its remapped value, otherwise, we use k itself. To ensure that this index won't be used again, we remap k in flipped_map to the index corresponding to remaining_zeros minus 1 or to itself if no previous remapping exists for that index. After updating flipped_map, we decrement remaining _zeros to reflect that one less zero cell is available. Finally, we convert the selected index in the 1D array back to its corresponding 2D coordinates using simple arithmetic. The row is obtained by dividing k by the number of columns, and the column is the remainder of k divided by the number of columns. This approach offers some important benefits. By using the flipped_map dictionary, we avoid the need to maintain the full matrix in memory, which saves space. Instead, we only store remapped indices, making the algorithm more space efficient. Additionally, the use of the remaining _zeros counter ensures that each available zero cell has an equal probability of being selected, maintaining uniform randomness. Now let's discuss the data structures used and their impact. The dictionary flipped_map allows efficient lookups and updates for remapped indices. This ensures we can dynamically manage flipped cells without excessive overhead. The single counter remaining _zeros simplifies the process of determining the range for random index generation. Together, these structures enable us to achieve an optimal time complexity of 1 for each flip operation, including random number generation, dictionary lookups, and index conversion. The space complexity is proportional to the number of flipped cells, so it's k, where k is the number of ones in the matrix. In the pseudocode provided here, we see the initialization of the solution class, where the matrix dimensions, total cells, flipped_map, and remaining _zeros are set up, as well as the start of the flip method, which generates a random index k. The flip method continues with the core logic of remapping indices. If the randomly chosen index k has already been remapped, we retrieve its value from flipped_map. Next, we ensure k is remapped to the value corresponding to the last available zero index, which is given by remaining _zeros minus 1. This dynamic remapping prevents collisions and avoids the need for physical swaps in memory. After performing the remap, we decrement remaining _zeros, updating the count of available zeros. Finally, we return the 2D coordinates of the selected cell by dividing the index by the number of columns to get the row and taking the remainder to get the column. The reset method is straightforward. It clears flipped_map and resets remaining _zeros to its initial value, effectively restoring the matrix to its original state. This ensures the algorithm can be reused for subsequent operations. The edge cases listed here emphasize the robustness of the implementation. For instance, with a 1x1 matrix, the algorithm ensures the single cell is flipped correctly, and reset restores it appropriately. When all cells have been flipped, the algorithm gracefully handles the condition where no zeros remain. And finally, reset ensures that uniform randomness is preserved for new flips after clearing all previous states. The algorithm's efficiency is further enhanced by employing dynamic remapping in flipped_map. Rather than physically swapping elements in memory, we remap indices dynamically, allowing us to avoid collisions while maintaining uniform randomness. This technique is both elegant and efficient, as it eliminates unnecessary operations. Additionally, by leveraging the dictionary flipped_map, we store only essential data, significantly reducing space usage compared to managing a full matrix. Altogether, these optimizations enable the algorithm to achieve constant time complexity for random flips and minimal space complexity, scaling well even for large matrices. The combination of dynamic remapping, space efficiency, and uniform randomness ensures that the solution is not only correct but also highly performant. This makes it a powerful approach for solving the random flip matrix problem in both theory and practice. Here, we start by importing the random module, which we'll use to generate random indices for flipping. The solution class is initialized with two parameters, m and n, representing the dimensions of the matrix. Inside the constructor, we calculate the total number of positions in the matrix by multiplying m and n. We also initialize a dictionary called flipped, which will help us track the indices that have already been flipped. Now, in the flip method, the first step is to generate a random index for our flattened matrix, which is essentially treating the 2D matrix as a single linear array. Using the random module, we generate a random integer between 0 and total 1. Then, we use the flipped dictionary to handle collisions. If the random index has already been flipped, we retrieve its mapped value, otherwise, we use the index itself. This ensures that we correctly handle cases where some positions are already taken. Next, we update the mapping for the generated index by assigning it to the value of the last available position in the matrix. This helps us efficiently manage the remaining positions. Finally, we decrement the total counter to reflect that one fewer position is available, and we convert the flattened index back into 2D coordinates using integer division and modulo operations. The method then returns these coordinates as the result of the flip. In the reset method, we restore the matrix to its original state. This is done by resetting the total variable back to the full size of the matrix, which is simply the product of m and n. We also clear the flip dictionary to remove any mappings, ensuring that all positions are available again for flipping. This method is especially useful when you need to restart the process of flipping without creating a new instance of the solution class. By resetting these variables, we ensure that the matrix behaves as if no flips have occurred, effectively starting over with a clean slate. Here, we start by defining the structure of our solution class. The class uses several instance variables to manage the state of the matrix. We have rows and calls to store the dimensions of the matrix, and total to track the number of available positions left for flipping. A hash map named flipped is used to handle collisions when we generate random indices, and the random object allows us to generate random numbers. In the constructor, we initialize these variables. Rows and calls are set to the provided dimensions, total is calculated as the product of rows and columns, and the flipped map is cleared to start fresh. Now, in the flip method, we generate a random number r between 0 and the current total. This represents a random position in the flattened version of the matrix. Using the flipped map, we check if r has been used before, and if it has, we resolve the collision by retrieving its mapped value. This ensures that we always get a valid position to flip. Finally, we prepare to update the map by associating r with the position at the end of the current valid range, represented by total 1. This helps us manage collisions efficiently as we reduce the number of available positions. After updating the flipped map, the total variable is decrement to reflect that one fewer position is now available for flipping. With total reduced, we convert the chosen flattened index x back into its corresponding two-dimensional coordinates using integer division and modulus operations. The result is returned as an array containing the row and column indices. This ensures the function outputs the position of the flipped cell in the original matrix format. Next, the reset method allows us to restore the matrix to its original, unflipped state. It resets the total back to the full size of the matrix and clears the flipped map entirely, removing all records of previously flipped positions. This makes the solution reusable for multiple test cases or scenarios without needing to create a new instance. Together, these methods provide an efficient and scalable way to handle random flips and resets in the matrix. To start, we are working with a 2x3 matrix, meaning it has 2 rows and 3 columns, for a total of 6 cells. We initialize several variables, self.m and self.n to represent the dimensions of the matrix, self.total to track the number of cells left to flip, which starts at 6, and self.flipped as an empty dictionary to keep track of the mapping for flipped indices. Now, for the first flip, a random index r is generated. For example, let's say r equals 4. We use the self.flipped.get method to determine the actual position to flip. Since the index 4 is not yet in our flipped dictionary, it maps to itself, so x equals 4. Next, we update the mapping by setting self.flipped, 4, to the value of self.flipped.get, 5, which is 5. This ensures that future flips will avoid the already flipped index. We then decrement self.total by 1, making it 5, and convert the 1D index x equals 4 to 2D coordinates. Using integer division and modulo, we find the row as 1 and the column as 1, so the output is 1, 1. For the second flip, another random index is generated, let's say r equals 2. Again, we fetch the position to flip using self.flipped.get, r. Since r equals 2 is not in the flipped dictionary, it maps to itself, so x equals 2. To update the mapping, we set self.flipped, 2, to the value of self.flipped.get, 4, which is 4. This ensures that index 2 now points to the next available position, avoiding duplicates. We then decrement self.total again, reducing it to 4, and convert the 1D index x equals 2 to 2D coordinates. The row is calculated as 0, and the column is 2, giving the output 0, 2. Finally, when we reset the matrix, we restore self.total to its original value of 6 and clear the self.flipped dictionary. This allows us to start fresh for a new series of flips. Now, let's consider a 3x3 matrix, which has 3 rows and 3 columns, for a total of 9 cells. We initialize the variables similarly. Self.m and self.n are set to the dimensions, self.total is initialized to 9, and self.flip starts as an empty dictionary. For the first flip, a random index is generated, such as r equals 7. Using self.flip.get, r, we find that r equals 7 maps to itself, so x equals 7. To update the mapping, we set self.flipped, 7, to the value of self.flip.get, 8, which is 8. This ensures the index 7 is marked as flipped and the next available position is tracked. We then decrement self.total by 1, making it 8, and convert x equals 7 to 2D coordinates. The row is obtained as 2, and the column is 1, which means the output is 2, 1. In the second flip for the 3x3 matrix, another random index is generated, such as r equals 2. Again, we use self.flip.get, r, to determine the position to flip. Since r equals 2 is not in the flipped dictionary, it maps to itself, so x equals 2. We then update the mapping by setting self.flipped, 2, to the value of self.flip.get, 7, which is 7. This indicates that index 2 is now flipped, and subsequent flips will avoid it. We decrement self.total by 1, reducing it to 7, and convert x equals 2 to 2D coordinates. The row is calculated as 0, and the column is 2, resulting in 0, 2. When we reset the matrix, we restore self.total to 9 and clear the flipped dictionary, preparing for a new set of flips. Finally, we explore an edge case with a 1x4 matrix, which has 1 row and 4 columns, for a total of 4 cells. The initialization follows the same process. Self.m is 1, self.n is 4, self.total is set to 4, and self.flip starts as an empty dictionary. For the first flip, a random index is generated, such as r equals 3. Using self.flip.get, r, we find that r equals 3 maps to itself, so x equals 3. To update the mapping, we set self.flipped, 3, to the value of self.flip.get, 3, which remains 3. This ensures that index 3 is marked as flipped. We then decrement self.total by 1, making it 3, and convert x equals 3 to 2D coordinates. Since the matrix has only 1 row, the row is 0, and the column is 3, giving the output 0, 3. Afterward, resetting the matrix restores self.total to 4 and clears the flipped dictionary, allowing for another fresh start. Time complexity analysis begins with the initialization process. In the __init___ method, we set up the matrix dimensions m and n, calculate the total number of cells as m*n, and initialize an empty dictionary called flipped. Each of these steps is straightforward and takes constant time, so the total time complexity for initialization is O(1). Next, the flip operation involves 3 key steps: generating a random index, resolving collisions using the dictionary, and converting the flattened index to 2D coordinates. Generating the random index is an O(1) operation, as Python's random.randint is highly efficient. Accessing and updating the dictionary, which handles collisions, also operates in constant time on average due to the nature of hash-based lookups. Finally, converting the index into 2D coordinates involves basic arithmetic operations, which are also O(1). Combining these steps, each flip operation runs in constant time, O(1). The reset operation also has constant time complexity. Resetting the total variable to m*n is a simple assignment, which takes O(1) time. Clearing the flipped dictionary by reinitializing it to an empty dictionary is also an O(1) operation in Python, as the old dictionary is simply marked for garbage collection. This makes the entire reset process extremely efficient, with a time complexity of O(1). Now, shifting to space complexity, the primary factor to consider is the dictionary self.flipped. This dictionary grows dynamically to store mappings of flipped indices to their positions. In the worst-case scenario, where all m*n cells are flipped before a reset, the dictionary will contain m*n entries. Since each entry is a key-value pair of integers, the space required per entry is constant. Thus, the worst-case space complexity for the initialization phase is O(m*n), which is proportional to the matrix size. For the flip operation, each flip adds one new entry to the dictionary self.flipped, which means the space used by the dictionary grows linearly with the number of flips. No additional auxiliary space is used beyond the dictionary itself. This results in a per operation space complexity of O(1), as each new entry only requires a single constant amount of space. On the other hand, the reset operation clears the dictionary entirely, reducing its space usage back to O(1). This is achieved without using any additional memory, as resetting the dictionary simply discards its contents, making it available for garbage collection. Therefore, the space complexity of the reset operation is also O(1), ensuring that the overall space usage remains efficient. Comparing this optimized approach to a naive implementation highlights significant improvements in both time and space complexity. A brute force method might maintain a full 2D array to track flipped positions, which requires O(m*n) space upfront. Additionally, a naive flip operation would involve randomly selecting positions and checking their status, potentially leading to O(m*n) time in the worst case due to repeated retries. In contrast, the dictionary-based approach ensures each flip operation runs in constant time, O(1), by leveraging efficient hashing for lookups and updates. The reset operation also achieves O(1) time complexity, making the entire process highly efficient. Space complexity is similarly optimized, as the dictionary grows dynamically and only uses memory proportional to the number of flips, with a worst-case space complexity of O(m*n). This approach balances dynamic memory allocation and efficient operations, making it far superior to the naive method. When working on the random flip matrix problem, there are several common mistakes to watch out for. First, inefficient random indexing can be a major issue. This happens when you repeatedly generate random indices without ensuring uniqueness, such as randomly picking indices and checking if the cell has already been flipped. As the matrix fills up, this approach becomes increasingly slow and impractical for large inputs. A better solution is to use a mapping technique, like a hash map, to track available indices efficiently. Next, memory overhead can become a problem if you allocate an entire M by N matrix to track flips. For large matrices, this is not only unnecessary but also consumes a lot of memory. Instead, you can simulate the 2D structure using a 1D array or mapping, which drastically reduces memory usage. Additionally, overlooking edge cases is another pitfall. For instance, failing to handle scenarios where all cells are flipped or when the matrix size is 1 times 1 can lead to infinite loops or incorrect results. Explicit checks for these edge cases can prevent such issues. Finally, mistakes in 1D to 2D index mapping are common, especially when calculating row and column values. Always use the correct formulas: row equals the index divided by the number of columns, and column equals the index modulo the number of columns, to avoid these errors. Another mistake to avoid is not resetting the state properly. If the matrix state isn't reinitialized when required, this can lead to inconsistent results, especially during multiple test cases or reinitializations. To fix this, ensure that you reset the mapping encounters appropriately. Now, let's discuss some interview insights. Scalability is key. While a brute force approach might be acceptable for small matrices during initial brainstorming, always consider how your solution will scale with the dimensions of the matrix. Hash maps are often the best tool for tracking flipped cells or available indices since they allow for efficient handling of uniqueness constraints. Also, be prepared to discuss space-time trade-offs in your approach. For instance, while mapping-based methods reduce space usage, they may add some complexity to the code. Demonstrating an understanding of these trade-offs shows depth in your problem-solving skills. Finally, always explicitly address edge cases in interviews, such as handling empty matrices, fully flipped states, or matrices with just one cell. This can make a strong impression and highlight your thoroughness. In terms of related problems, there are several you might want to explore. LeetCode 384, Shuffle an Array, involves similar randomization concepts but focuses on arrays rather than matrices. LeetCode 380, Insert Delete Get Random O(1), is another relevant problem that deals with efficient random selection using specific data structure techniques. Of course, LeetCode 519, Random Flip Matrix, is the exact problem we are discussing here, so mastering this is crucial. Additionally, LeetCode 528, Random Pick with Weight, introduces random selection with constraints, which is conceptually similar when it comes to index manipulation. Now, looking at alternative approaches, the brute force method is the simplest to implement. By randomly picking indices and checking for flips, you can achieve the goal, but it's not efficient for large matrices because of repeated random generation and checks. This approach is straightforward but comes with high memory usage and poor runtime efficiency as the matrix fills. On the other hand, mapping with a hash map provides a more efficient solution. By maintaining a mapping of available indices to their flipped counterparts, you can randomly select indices from the available pool and update the mapping. This method is significantly faster but introduces additional complexity in implementation and debugging. Finally, an optimized approach involves treating the matrix as a 1D array and performing flips using direct index manipulation. This technique is efficient in both time and space, as it eliminates the need for a full 2D representation and avoids redundant checks. However, it requires careful handling of the 1D to 2D conversions to ensure correctness. By converting indices accurately, you can achieve a streamlined solution that balances efficiency with simplicity. Each of these methods has its trade-offs, so understanding when to use them and being able to articulate why you chose a particular approach is essential, especially in interview settings. That wraps up our walkthrough for problem number 519, Random Flip Matrix. We reviewed the brute force approach, discussed complexities, and shared key insights about tackling randomization problems. Don't forget to like, share, and subscribe for more content. Thanks for watching, and happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!